Today we're going to speak about intrinsics. The good, the bad, and the ugly was something that Harald forced upon me to have. No, just kidding. It was something I wrote. Who am I? My name is Anders. I work as a COO for a company trading US equities. I'm allowed to program, yes. So even though my title, I code a lot. I'm one of you guys. I have a background in programming various languages, and that's what I do for a living, basically. So I'm guessing a majority of you guys are in the same boat in that sense. So normally I'm sitting there somewhere. I'm looking at you guys, presenting these fabulous presentations. I got tricked to stand up here. I don't know how I feel about that. We'll see later. But when I see a lot of familiar faces here that are usually on stage, we'll see how I manage. So let's start. We all programmers. We have a task and we use a language or we use some sort of tools in order to kind of get to our goals, right? My guess here is that a lot of people tend to lean towards C++, but myself, I use Swift sometimes. We all use Bash and so on. So we will speak about one tiny thing that we can access using these languages. But just to set the stage, I have a couple of slides I just want to go through before we dig into the deeper parts. So we have one thing that we talk about sometimes as performance programmers. Some of you guys are, some of you guys are not. I spoke to one old friend of mine just over here when we started, and he was talking about the kind of power they could get out of modern computer systems, writing the correct code and maybe not having Electron applications, layers and layers and layers and so on. So we need to kind of speak about the need for speed. And this is something I encounter from time to time. There's some guy who's like, he parses trillions of rows or whatever, and if it takes 1 week or 1 week and 1 hour or almost a week, whatever. And that can happen there are a lot of people I encounter where I am. Everything in this presentation is, of course, my worldview. It might not represent yours, but you produce a lot of data, and then you need to deal with the data. So if you produce it in 2 seconds, and then it takes a lot of time to analyze the data, it's just going to stack up work, right? So the need for speed is also related to how does your chain look like, your production chain or the workflow. So I'm just going to relate to the places I've been at where you need speed. You for example, when I've been working with video processing, you got like 20 milliseconds, and then you get a new picture. And if you haven't dealt with all the data, you get a new picture, you get a new picture. There's no way around that. You need to be able to deal with a lot of data, because if you're not done, there's just data thrown at you all the time. So, for example, this is maybe a ridiculous figure because we don't really do a lot of 8K productions yet. But one single image is like 33 million data points, and they throw it at you at 60 frames per second. So it's like 1.9 billion data points you need to deal with per second. So it's a lot of data, right? Or in the financial domain where, you got some data and you got some nanoseconds or maybe microseconds or something to make a business decision, right? So you get like maybe a tiny piece of data, and then you need to make something smart out of it because there's new data coming. And if you haven't taken that decision, or if you made the wrong decision, it's also the same thing as media almost. It's a real-time data flow. And those are the locations where I kind of encountered where you need speed, right? And I'm not saying that, Python or C++ or that they are slow languages. It's just that some applications you need some extra speed. You need to really level up, right? And then there is something called SIMD. I mean, it's a weird tool. If you remember that old toolbox that I showed in the first slide, it's like the hammer. It's like, so this is looking a little bit funky, right? But it's still a tool, right? And if you look at, I don't know how much you look at, for example, hacker news. Sometimes there's like, oh, this dude, he made this in SIMD, and it's like 5,000 times faster or whatever. So I was just browsing the net, fast SIMD, and then just took some headlines. But you parse gigabytes of JSON. You do speed ups of 800%. In NumPy in Python, Intel published a sorting engine, and it's like super fast. And they implement it, and then you're good to go, right? We'll speak more about SIMD, because I don't know how familiar you are with these terms, but SIMD is a single instruction that is actually processing a lot of data. So that's a single instruction but multiple data. And there are a couple, we shouldn't forget, there are other things in the intrinsics world as well. For example, advanced matrix extensions from Intel, which is basically a matrix multiplications and so on. They're coming out with some funky stuff. Really, really advanced stuff, Intel. And it's, of course, triggered. This is my wild guess. AMD, NVIDIA, skyrockets, GPUs, machine learning, valued at NASDAQ like I don't know what. So there's, it's a good business to be in, right? So if you might make the right tools, you're going to be up there with those AI machine learning guys. I don't know. That's what I'm thinking. There are also, there's a whole list of stuff you can access, and the compilers are doing that as well. It's not that we don't use this, it's just that we don't access them normally, directly. Bit manipulations and so on. There are, of course, in C++ standard, bit manipulation that under the hood is probably using that if you use CPUs that are capable of those instructions, of course. So I don't know if we agree, but I hope we agree that the more speed we can squeeze out of stuff, the better. But there's also a lot of people that are we're doing plenty already, and it's good enough. And that's fair enough. You're obviously happy with where you are. You should be. But for the sake of this presentation, we take a decision to gonna go down into the cave, and we're gonna look at what's down there. So there is another thing that we also need to kind of take into the equation. It's like, I got something slow, and now I'm going to double the speed, or I'm going to do this. It's probably, based on salaries and based on, not in all cases, of course, as I say, but sometimes it's just better to buy a faster CPU, get a faster memory, do hardware upgrades, don't code, just buy the next generation, So that's the low-hanging fruit. But we as programmer, let's be smart about it. And you might have seen this before, and of course, it's obvious to you. It's not like, like trying to learn dad how to make, children. I don't know, but you kind of, I still want to talk about it, because you have a big gain in the infrastructure. If you're on a network and it's 10 megabit and you're on a network that is like 100 gigabits, of course, just being on that faster network will speed up stuff, right? Or disks or CPUs, Then you have the algorithms, it's super fast code, but you're doing it stupid. I mean, it doesn't make sense the way you're doing it. So, but the higher you go into the pyramid, it's like that's a little bit where we are, right? So we think about algorithms, how to implement them, and also how to kind of execute them in code, right? So with that said, let's look a little bit, what we have to play with here. So I don't know if you're familiar with that, if you've seen this. It's thrown out or thrown up on presentations from left and right. It's the orange triangles are the transistor count basically, and it's Moore's law more or less. And you can see that the frequency kind of leveled out. Single thread performance, it's still going up. If the last time I looked at it, it's that a single core performance increase is about 6-year cycle, and it will change, of course. But as we are right now. And then the number of logical cores is of course is growing. I mean, we have seen that the last couple of years. I'm running machines where I work right now, where we have like 256 hardware threads, and AMD are releasing all the time, more powerful CPUs, right? There's also another thing that we as performance programmers end up with. It's like there's a gap with we talk about faster CPUs. It's like not maybe gigahertz now, but we're optimizing these things, and we're moving things in and out from the memory. And sometimes it's a blocker because memory performance, processor performance is a gap. So we need to be smart about how do we move stuff around, caches, whatever, you know these things. So if we start digging down into these guys then, so you maybe have seen pictures like this where they kind of try to analyze, they take one Intel core and then, or the CPU, and then they kind of, these are the memory controllers and these are that. And you can see that there's a section here, quite large, if you look at it from a percentage-wise, that is saying SIMD. So obviously, I mean, they're throwing processing power on that. It must be a value, right? I mean, every single transistor is like valued a lot for these guys, and there's a big block here saying SIMD. So let's hope it will bring us some speed. So with that said, how can we get hold of them? And there are a couple of ways we can do that. We write our code just like we've done, forever, and then we say compiler switch. We might say 03. Normally, we release something. It will actually vectorize for us. If we have a target where we have a CPU that can vectorize, it will vectorize. If we say that it's just a generic CPU, it will not use any vectorization. So then some compilers, like the Intel compiler, has pragmas. So they, in a loop, you can say, because it might be difficult for the compiler to understand the exact underlying data structure, so you can tell it, the data is ordered like this. So you help the compiler to vectorize. Then you also have the special compilers. I don't know if you have ever looked at ISPC, that compiler. It's an Intel compiler. It actually compiles C code. So you write something in C code, it vectorizes it for you. So it's quite powerful. And by the way, I'm just babbling on here. If you have any questions, we don't have to wait until the end. Just ask them as we go along, of course. Or you can use OpenMP and have a CPU as a target, and it will vectorize as well. There are SIMD classes, so you can look on GitHub, or there are various sources where you can use helpers. Basically, it's templates that will vectorize things for you. Normally the basic stuff, and it's very, actually it's super advanced. I shouldn't say it's simple. These guys have been working hard to simplify the complexity for you, so you can work on a more abstract layer. But we will talk about intrinsics today, just as an introduction. introductory, how to get hold of them, how to work. This will take too long to speak about all this. So we kind of focus on this today. See if Harald lets me in again after this. So, and of course we can use assembly blocks in the code, which is, I've done it. It's very, I don't have a very good experience with that, especially if you start writing complex things. So I gave a hint that you have to have a specific target to access certain things. So in SIMD there are various versions that Intel and AMD has released. Started with MMX, then came SSE, versions of SSE, then AVX came, AVX2, and now we're at these AVX 512. And as you can see, the years we have there is where they released CPUs. So a normal target for me is the Haswell, or actually it's Skylake I started using right now. But it's been Haswell a long time for me to access the AVX2 instruction set. And there you need to think a little bit. I mean, you have your code and then you have your target. You have your, depending on what you're accessing or what your target is. Is it only new stuff? Is it old stuff? You don't know. That's a decision you need to kind of make when you write code like this. And you can use compile flags to access the new stuff, or you can just leave it. Then you get the old stuff, right? Or you can make an in-between thing where you use compile flags and runtime switches, where you kind of look at the CPU ID registers to look at what am I running right now? Am I running on something that can do this? And then you can, of course, execute code that can run on that. So you can. It depends on the what path you want to take here, and it has various advantages and disadvantages, of course. So the target, I've been talking about the target. It's on, you can use on GCC. You can, for example, use the March native, which is, the stuff you're running on. Or the target, if it's March equals Skylake, then it's going to be targeting the Skylake. Or you can target the actual AVX or AVX2 or AVX 512 with switches as well. There are different switches for different compilers. So that would be GCC and Clang. While the one that says Arch would be for the Intel compiler, so Microsoft's compiler. And then there are also other flags to vectorize loops and things like that. That are implicitly enabled as part of the optimization flags you have. Yes, go ahead.
Question, Anders.
Of course.
One thing I've wondered about since I've heard about these things for a long time.
Yeah.
It had to do with chess programming in that case.
Hmm?
My general question is that if you compile with one of these fancy flags
Yeah.
and you deploy it on a CPU that doesn't have these fancy instructions, does it fail or does it fall back to some more primitive instruction?
No, it will fail actually. So it will be an illegal instruction. So that's why you need that one. You need to really be aware of, so to say. I mean, you can understand that. I mean, there's no one who knows what an instruction looks in the future, right? So it will not work basically. So you have to deal with it in this type of manner, in that way. And in runtime, there is a. I mean, we run into this from time to time. We target code using different compilers, and it's different switches and different pragmas and things like that. So, for example, if you use GCC, they have a built-in. You basically initiate the built-in CPU in it. Okay, and then you can use if this CPU that I'm running on is having this. Then I can run this code. It helps a lot, but I don't know exactly what CPU sometimes, or if I have this compiler. So I'll show you what I do. And And also, in order to get hold of them so that the compiler kind of resolves the pre-compiler and everything, resolves everything, you need to include header files, right? And it's also a little bit interesting, right? Because it would be easy if someone said, you call it this, but, there is one thing I actually missed from a previous slide that I noticed here. It's like the SIMD. I'm going to talk about the x86-64, the 64-bit Intel versions. There is the Neon version. It's the AMD. So inside AMD, there is a equivalent system that's called Neon. So if you're programming Intrinsics and your target is an ARM device, it's different set of header files that you have to include. And it's a different instruction set. It's different, layout and the way Neon works. So that adds to the complexity. If you're going to be like writing portable code in Intrinsics, it's going to be a little bit of work, you have to, but it's going to be fast, but it's going to be work, Work fast, no work. It's like going to school, right? You can skip going to school and you can get a work, but it will not be high paid, right? Or you work a lot and you get reward for that. It's the same thing. So, so I wrote there is a Intrinsics guide from Intel. I don't know if I'm linking it here. I'm going to do that later. So there is a nomenclature that they use. So if I look at the website, if I look at what this thing is doing, it's the same thing. It has a one-to-one mapping, right? So if it says that, it's the same thing in my code. There is a lot of like CPU detection, open source things out there, but they say like, you got this, but it doesn't match exactly what it says on the Intel website. So then it becomes like an interesting challenge to find out exactly what they mean, right? So I wrote that it's a header only. You can ask, I'm running on this, what does it have, basically. And there is also a document I recommend that is called the Intel C++ Intrinsic Reference that goes through all these weird things that we're seeing here. And for some of you guys who's working with Intrinsic, it's like, I work with this every day. It's nothing weird here. So what we're targeting when we're targeting these SIMD instructions are vector registers. Those vector registers comes with different size depending on what versions they are, AVX, AVX2, AVX 512. And the 512 is basically meaning that the register in size is 512 bits wide. So the 256 byte register in C++, when you write that, or in C, you would not call it int. You call it this, and that will kind of give you the access to this 256 bit register. That's 32 bytes, or what is it? It's 4 doubles or something like that. And there are also, these things that are part of the AMX, which is a vector of, it's a two-dimensional matrix. So you do a matrix multiplication, right? So you have this, and you call it, input 1, input 2, and then you matrix multiply them together, and it's hardware optimized in the CPU. But you have to, in your language, you have to kind of define exactly what type of data, what am I giving, what is it processing. So this reference, those registers, and understanding this is part of, getting hold of these suckers, or whatever I can call them, And this is the Intrinsics guide that they have on Intel, and I'm just going to go through it a little bit so you can go home, and if you haven't looked at this before, some of you guys might look at it every day. But you have these instruction sets that you're interested in, and so that's the red arrow. And then you have a specific instruction set, and you select that, and it's the orange. And then you might want to look at a specific instruction. That's the green arrow. And then there is the actual intrinsics syntax, which is the blue arrow. And then it's the black or dark blue arrow, which is basically which header is, where do I find this? Which header do I need to include? And then the purple one is the assembly instruction for that specific intrinsic. And then it's the CPU ID flag you need to get. So that one would correlate to the header file that I spoke about earlier. So if I need that instruction, I need to find out that, okay, I got this. Cool, then I can access that instruction. So, and this specific instruction, I don't know how we are on time, but you know, hopefully we're okay. Harald had to shout at me if I'm not. So you can extract bits. So you have a 64-bit register, and you can pick bits that you would like to extract from that register, and it collapses to the lowest least significant bits and builds up from there. So there are a lot of these guys that sometimes, you know, the compilers are using, of course, but sometimes, you know, we would like to get hold of them ourselves because of various reasons. You know, and it's, I don't know how you see this, but it's, to me, it's huge. It's like super complex. And if I read this text, sometimes it's like, I don't know. I don't understand what they write. And they have been thinking, you know, what should we write here to make it understandable? It's very difficult, right? So, yes, there's this dude who made a super website. And you basically just select the instruction that you would like to know about, and they visualize it. Oh, it's like, you know, for me to see something, to understand, it's like, that works for me. So this is something that is dealing with a 128-bit register. It has 16 bytes, right? And it has, this is how it looks. It outputs a 128-bit register. This is the command. It has an input of 128 bits. Then it has two other things. Okay, so what are the two other things? Well, I kind of made it maybe more readable out there. So you have the register. Then the instruction is inserting a byte somewhere in among these 16 bytes, right? So it takes the data, which is a 32-bit probably. Yes, 32-bit. And it takes the lowest 8 bits out of that register. And then it's using the nibble in the position. So it takes the last 4 bits to determine which, you know, position, where should I insert this? You know. So it's you know, I don't know. I shouldn't maybe oversell it. Yes, this is Stack Overflow. Yeah. No, sorry, I didn't understand your instruction. Okay. So, should we? Okay, let's put some of this stuff into play. I mean, for real, let's compile some stuff and work with it and see how it works and see what kind of speed ups we get. And I must thank, you know, everything I do when I go to work. You know, it's like we do this super fast stuff, and it's also super secret, so I can't show anything. So I asked one of the employers to you know, could I play around with this? Could I show it? And they allowed me. So I'm really grateful for that, because else I would be empty-handed here. Okay, I had to remove all the comments. Oh, it's not showing up there. Where is it? Is it coming up here? Yeah, good. Oh, this is going to be interesting. Now I have to... So this comes with a lot of comments, but I had to remove them. I'm sorry. So this code you're kind of relating to, right? I mean, it's C++, call it whatever, right? And we were doing some timing, and then we're doing some stuff. And then we're doing it in a C function, right? So we have some C function that is doing something in C. And then we have the equivalent in AVX2, right? So this would be the code that is doing the exact same thing, right? And then we benchmark it, and we see what kind of speed ups we get. So let's do that. We have, I hope I can connect to this server somewhere in the world. And it runs the tests. And the decode name function was, I got a 389% increase by doing AVX2. That's the, compared to the optimized C version, and the 900% faster to do this specific function. So as a developer, when I work with this, it's this would take some time to write. It's quite fast. I mean, it takes a little bit of thinking. You write it, you leave it. This one, I don't know. It's, to me, I don't even know what I was thinking when I was doing this. It's like, to go back to old AVX code, it's like starting from square one, It's super fast, but it's like, what the hell did I think here? How, it takes a long time to kind of get back to that. But, this is the reward, this is where you get to. This is like super fast stuff, A lot of people are saying like Rust, it's like blazing fast library, Rust. Sorry, this is fast. But not everything can be vectorized, so you should be careful with saying that this is the one tool, But it's one of the tools, as I said. Sometimes I use this, sometimes I use that. It's just, it's fast. Okay, so let me see if I can get back my screen here. So just kind of. Looking back a little bit, I've been programming for maybe 10 years. No, I've been programming for many years. But the first time I saw it, I didn't even know that it was existing, but I used it a lot. I started programming on a CPU called Motorola 68000, old, probably developed in the 60s or 70s, something, from Silicon Valley. It had one of these instructions that we used all the time. It's like this instruction moved a lot of memory into all the registers. It was like one single instruction, and we used it, to move a lot of data around. So it became like our powerhouse, and it was actually a single instruction, multiple data, right? So it's been there for a long time, and I was thinking like, yeah, that's like, it must have been the first, right? But actually, Cray. 1975 or somewhere around there. That's, SIMD. That's where it started. At least when I read the history, it might have even older history. But Cray 1 had SIMD instructions. So it's been there for a while. I kind of already went there. I made some code to kind of pixel convert from various, resolutions in color, and I've, getting back to this is like, maybe it's interesting, So wrap up. Let's go, right? So everyone here is in, like tomorrow, I'm going to start writing Intrinsic. I'm going to try to convince my boss that, I heard this speech yesterday, and they're probably going to go like, I don't know about that. and your team is going to go, dude, that guy is insane. We have to get him out there. He has to start in the Python team or something. Well, we'll see. But hopefully I at least was able to share my view of something here. So what's up in this world? Oh, check this out. You have seen this before. It's actually something that they work on in the standardization, and at least from what I read, I'm not as into standardization of C++ as maybe many of you are. But what I can read is that they are aiming for C++ 26, and it's going to be interesting because what I've been working on is very specific. You do it in this specific way, and there's a deterministic execution cycle and things like that. However, if you make it very abstract, it will be, I'm going to follow this. This is going to be super interesting. How can they be portable? How can between different compiler versions have a consistency in performance and things like that? So I mean, you ship something and then there's a new compiler, and then you compile some old code that you forgot, and suddenly you have in your hot path you have a totally different behavior. We'll see. Then as I showed you the ladder with CPUs and what type of vectorization they supported was very fragmented, right? So Intel has, there is a work going called AVX10, which is trying to kind of help us programmers to minimize the fragmentation of vectorization. We'll see. I mean, it's released in August. There's a lot of people in different forums who speak about this. There's a lot of knowledge about this which I cannot provide. I just know that it's happening. So it's something maybe interesting for you guys to look at. So we started with good, bad, and ugly. I don't know. We wanted speed and we got speed. That's normally when I've been working with SIMD and intrinsics and things like that. It's to really squeeze out all the juice from the CPU, and I've been able to do that. You get direct access to specific things. You pass all the layers and then bam, this guy, and then you suck it out. You're in a competitive world. Some people are not, some are. You make a product. If you can make a product that is doing 20 while the competition is doing 5, maybe you have an advantage compared to the competition. I don't know. Or just that you can do it. I mean, I've been working a lot with people that came from the hardware. I started also from hardware design and FPGAs and things like that, and it has been what has happened in the software industry the last couple of years, or maybe 10-20 years, is that it's been, I mean, you saw the just power software can have. I mean, stuff that was only hardware you can do with software today. So it kind of, but it's complex. It's not always fastest or compensating for the extra work. I mean, you have to spend a lot of time writing these vectorized things. I mean, at least I am. Maybe you're super fast, but I'm. It takes a lot of time to develop these guys, and it's not portable. And if you make it portable, it's going to be even more complex. And I've said this too many times now, but do you remember what you did before when you get back to the code? And the last thing before I let you guys go is this is a really good, you should read it, at least if you're into, optimizing stuff. It's a good, insight to the, what's happening under the hood, how can you work with different data structures, and, I'm just guessing now, but if you're writing a compiler, you know the inside and out of this document. I think it's well written and well spent time. So that's it. And yeah, sorry. So, well, if you have any interesting projects, or if you want to speak about optimizations and intrinsics and so on, I'm available on LinkedIn, or drop me a mail or whatever. So, do we have any questions or regarding this?
So
yes.
You had a slide in the beginning about what about CUDA?
Yes.
What would you say? Why should I not just use
CUDA? Yes, exactly. I'm a GPU guy. So this presentation, because of I noticed when I was making it, the complexity and the time it would take to just go. So I was just like, let's just focus on x86, 64, for this particular. But I totally agree. If I were to, it depends on a little bit. I mean, it's an interesting question actually, because if I've been in situations where you get something, you're in the CPU, you have the data in your hand, it's in the cache. There are Intel CPUs and maybe AMD as well that intercepts the PCI bus to put it on layer 3, on the layer 3 cache. So you got the data there. Then you need to transport the data over a PCI bus to the GPU. It might not necessarily in all your cases be the fastest. But if you have a massive amount of data like video processing, this is the go-to guy. I mean, we wrote we were decoding about 5,000 FPS of video on like a consumer GPU. I mean, nothing beats that. So this is actually my go-to guy. But it's just that, let's talk about SIMD. but it's also special cases. Like I had one case where, we got the data and we were doing some work in the CPU, but because we had the data in the CPU, actually the pre-processing that we were thinking about doing in the GPU was actually, because memory is slow, right? So we were spinning around memory in the CPU and then we shipped it up to the GPU. So we did a multi-stage processing. So I wouldn't rule out SIMD. It can actually work in conjunction with CUDA, but CUDA is much faster. In the applications I've been in, if you're going to make some recursive stuff, it's probably super slow. Yeah. Yes.
Yeah. When you make software to ship to consumer computers,
yeah.
In 2023, you can't always assume they have Intel processors because of Apple Silicon and stuff.
Yeah.
And that makes it twice the amount of work to run
yes.
the functions. So I'm very curious about, you mentioned the SIMD classes or whatever.
Yes.
That abstract this a little bit.
Yes.
What's your experience of using those compared to using the native intrinsics?
Okay, so I've actually just looked at one. There's been in CPPCon, forgot the name of it. Unfortunately, I should have name dropped that one. There is one guy that has made really, really good SIMD presentation that is talking about his class. But it has always been x86-64. So with that said, there is a repository on GitHub that can convert the x86-64 SIMD to Neon. So if you're interested in that, we can speak after. I can give you some pointers. I don't have it in my head, but you can basically say, I'm writing this code, let's write it in Neon, and it will basically just convert it for you by using the intrinsics that you write for the Intel. It will just port it over to Neon. Then, if it's going to be best, I have no experience with that. I just seen it because I'm in the same situation. I obviously, this Apple device. They make a great Intel, the Rosetta, but it doesn't support AVX2. It's only AVX, and that's why I was running towards a computer somewhere in the cloud when I was doing. So I'm perfectly aware about your problem. And the best answer I have is look at that conversion. It will save you a lot of time. Yes. Okay, cool. Thanks.